Yeah, well, thank you everyone for joining us. I'm Brett. I'm a faculty in civil and environmental engineering. I'm one of the three directors of CS4Env, the newest one. Vikram is another, and Marine Denol is not here today, but typically is. So our speaker today is William Eek. He's a PhD student in atmospheric sciences here at the UW. He previously did a BS in math and computer science at Harvey Mudd. And his work, as you can tell, is at the intersection of climate modeling and machine learning. So with that, I'll hand it over to William. And maybe you could minimize
Oh,
the,
that's a, yeah, I forget that everybody can see that as well too. Why don't I just do this?
perfect.
Put myself in the corner. Okay. Great. Well, thanks everybody for coming. Yeah, I'm Will. I'm a second year and I work with Dale Duran in the Department of Atmospheric and Climate Science. Excited to be here to tell you about the work I've done so far while I've been here on evaluating a deep learning weather prediction model with a baroclinic wave test on Planet. It's a lot, it's a big hunk of a title, but I hope that by the end you'll have a sense of what each of these individual words means and how we can put them together to make sense. Okay, so I'd like to start this talk with a brief overview of numerical weather prediction, machine learning for numerical weather prediction, and how we evaluate both of these types of models. Okay, so the traditional paradigm in numerical weather prediction is that we write down our best estimation of the governing equations of motion in the atmosphere. They're partial differential equations. We discretize them vertically and horizontally on a grid, something like this, and we solve those equations using large supercomputers. They have to be large because we often want to have very fine resolution in both the vertical and the horizontal direction. And so around the world, governments have supercomputers that are sort of dedicated to solving these equations on the sphere. There's lots of processes involved here, such as advection, radiation, interactions with the ocean and the land. And so having all of these processes sort of combined into one model increases the computational cost of this. And there's even processes that we can't write down explicitly because they interact on scales smaller than the individual grid box size. And for those, we have to use approximations. So with the advent of a lot of historical weather data becoming really easily available, machine learning has offered a computationally cheap alternative to this traditional paradigm. Jae-Yoon Chen is raised. Is there
Could you share
something
the screen? We cannot
wrong
see
with
the screen.
in the
So
Zoom?
people on Zoom are saying they can't see your slides, but we are able to
It's
see
that
it.
like only hosts and co-hosts can see what's shared.
Oh, it's in.
Oh, is it? Okay. Let's see.
Yeah, because I can see it there.
All
but-
participants. Does that work? Yes. Yes.
Great.
Cool.
Okay. Sorry
Okay.
about that.
Sorry
Sorry
for
about
that.
that, people on Zoom.
That was our fault.
Now you can see what I see. They can see what I've been talking about. Okay. So traditional numerical weather prediction is costly, but it's been the way that we've been doing things for a long time. In the new age, machine learning is offering an alternative, an attractive alternative, because we can just train it based on millions of examples of historical weather data. We have examples of the weather now, and then we have a bunch of examples of the weather 3 or 6 hours later, and we can use these examples to train a machine learning model, like we do for other tasks like image recognition. So at this point, the technology has gotten good enough that these machine learning models are matching or outperforming our best numerical weather prediction models. To highlight this, I'm going to show you a plot of a bunch of different machine learning models for weather prediction with publication date on the x-axis and skill, sort of skill at 3 days for an important weather variable, which we call Z500. The details aren't important there, but relative to our best numerical weather prediction model, generally what is regarded as the best numerical weather prediction model, which we call the IFS. So a score of 100 there, showed in the dashed red line, means that we're matching the skill of our best traditional model. So since first attempts of this for machine learning on weather prediction happened in around 2018, 2019, skill pretty rapidly increased over the next few years. But really since 2023, there's been an explosion of models from a bunch of different institutions. These are government institutions, these are large tech companies like NVIDIA and Google, these are small startups. There's been just an explosion of models that are now outperforming our best sort of models here that I've talked about on the left. And it's not just performance on certain key metrics, they're actually being used for real world applications. So there's a nice article from the Wall Street Journal talking about how the Indian government actually used some of these AI weather models to send out forecasts from the monsoon season from their farmers. And there was actually a lot of impact made sort of with the help of better models that they had, and it's sort of at the speed at which they could deploy them, because these machine learning models are quite fast. Here in the United States, our National Oceanographic and Atmospheric Administration is sort of experimentally using some of Google's hurricane tracking models for this upcoming hurricane season in conjunction with their traditional ones. So it's sort of an experimental phase, but they're really looking into this. So not only are these models good, but they're also very fast. As I said, traditional numerical weather prediction models, you need a supercomputer in order to run them. But machine learning models, once they are trained, just a caveat, once they are trained, are very fast. They can be run on something like my laptop here, and you can get a 14-day forecast of the weather in just a matter of seconds. One really large caveat about machine learning weather prediction models is that they're black boxes, as is the case with a lot of machine learning models, and that they contain little to no explicit encoding of any physical laws or constraints. So we haven't written down explicitly any sort of governing equations of motion of the atmosphere. So they're doing really well, but they somehow don't have an explicit notion of physics in them. And this poses problems for several reasons. The first is that as people who study a physical system, the atmosphere, we know that there are governing equations. We know that there are, there's a way that we know things work. And so it's sort of unsettling. It was like, why are these models able to make the predictions that they do? We'd like to understand this from just a simple trustworthiness. Do you want something that can predict the weather if you don't really know how it works? There's also the fact model intercomparison. There's lots of different models which are now outperforming our best traditional ones. How do I choose which one to use? Is there a reason why one might be better than the other? And then these models are also starting to be used for longer timescale prediction. So beyond just 2-week weather, we want to use them for seasonal to subseasonal prediction, or even climate timescale prediction. But on those larger timescales, we expect the distributions of, say, temperature and humidity and precipitation to shift both in magnitude and in sort of space. And machine learning is not really known for extrapolating very well to examples beyond its training data. So will these models continue to make good predictions of the weather in a warmer climate in, say, 2075? These are things that we'd like to know, but it's hard to, because these machine learning models are black boxes. Okay, so the question that I'm going to ask for this talk is, how can we build confidence in the learned physics of our machine learning models? Are they extracting the correct atmospheric physics out of the training data, or are they just finding simple correlations that won't be applicable, say, on longer timescales, or just aren't physical in some way? And so the argument I'm going to make is that we can do this by testing them in the same way that we test our traditional models. And sort of this is an art that's sort of been lost in the last few years with the development of machine learning models. So traditional models are usually evaluated on a hierarchy of tests. You test the simplest components in the model, and you add successive components, adding more complexity, more processes, until you reach sort of the final stage of your model that you've gained full confidence in. So the least complex test that we do typically with our atmospheric models is that we first test them on what we call 2D shallow water experiments. We approximate the atmosphere as just this very thin layer of fluid on the gigantic Earth. So the height of the fluid is very small relative to the horizontal scale of the Earth. And here we're just testing sort of horizontal exchange of motion. Then after you've tested this, you can move on and sort of add vertical motion, and you can start to add moisture into the equations. From there, you can test things on what we call an aquaplanet to provide realistic boundary conditions. Here, to visualize the aquaplanet, when I was making this, I was remembering the scene from Interstellar where they're on an aquaplanet. And sort of, the sea surface provides a good boundary condition for the atmosphere. And so sort of this is the next step in the hierarchy of our testing. From there, you can add in land and sort of add in the sort of double boundary condition of land and the ocean and how those interact with the atmosphere. But you're fixing sort of the sea surface temperature, so you don't have a dynamic moving ocean. And then finally, you can couple the whole thing together. You have the atmosphere interacting with the dynamic ocean, maybe land and chemistry if you want. So this is the hierarchy of tests that we test traditional models on. But the problem is that machine learning models are typically only evaluated at the most complicated stage of the hierarchy. Because they're trained on historical weather data, they sort of they're trained on all of these processes together. And so we haven't really taken a step back and made sure that they satisfactorily pass the earlier steps in the hierarchy. So for this talk, I'm going to be focusing on sort of this middle range of the hierarchy, where we're evaluating 3-dimensional dynamics on the aquaplanet. So we removed the land part of it. These types of tests are typically called baroclinic wave tests. I'll explain what the word baroclinic wave means in a second. But the important thing here is that we're doing this on an aquaplanet because it provides sort of an idealized sandbox for us to test these models. By removing any dynamic ocean or any sort of land atmosphere interactions, we're sort of simplifying the problems so we can get a better sense of how the model behaves in an idealized setting. It also allows for more traditional apples to apples comparisons with our physics-based atmospheric models, because these types of tests are routinely run for these types of models during their developmental cycle. So we have sort of existing runs of traditional models for these different types of tests. Okay, so now I'd like to tell you about the test that we're running, which comes from Bouvier et al. So the baroclinic wave test sort of comes in two parts. I'm going to give an overview of the test as a whole and then sort of dive into the details of each part specifically afterwards. So it's a two-part test, and the first part evaluates an atmospheric model's ability to maintain an unstable steady state. Essentially, what we're going to do is we're going to set up our atmosphere like a ball on a hill, where the ball is still if you don't touch it. So the atmosphere isn't going to have any really interesting weather going on. But if you touch it just the tiniest bit, sort of the ball is going to go rolling up the hill, and some interesting weather is going to develop downstream sort of irreversibly. But at the beginning, if you were able to keep the ball on top of the hill in this very delicate steady state, then nothing's going to change. So the first part tests essentially your model's ability to do this. And if it is able to do that, then the second part, you evaluate its ability to correctly propagate your initial kicking your ball off the hill. So if you move your ball off the hill in a sort of a controlled way, you test the model's ability to propagate that instability into a full-blown storm. This type of storm is called an extratropical cyclone, and we see these are sort of storms that exist in the real world. This is the bomb cyclone from last year, which probably the weather of which affected many of you. You took out your power if you're living in certain parts of Seattle. So essentially, yeah, we initially test the model's ability to stay still, and then we test its ability to grow an instability into this really large storm. These types of tests are called baroclinic. The term baroclinic just means that the energy which is used to generate this storm comes from the temperature gradient which exists in the mid-latitude. So you have a tiny instability, and then it draws from the potential energy that comes from the temperature gradient in the mid-latitudes in order to spin up this gigantic storm.
Quick question about this. So these are tests where like our traditional weather models would or should be able to do these things.
Yes.
And we want to make sure that ML wants
Correct.
to do that. Okay.
Yeah. So machine learning, traditional atmospheric models are these sorts of tests are used in the developmental cycle of traditional models to make sure that there's a sanity check, that they're doing the right thing. But people aren't really running these tests for machine learning models. They're just, sort of evaluating them on real world weather prediction. Okay, so let's talk in a little more detail about this first part. So our background state here, our stable atmosphere, is going to be two jet streams on an aquaplanet. So the jet stream is this band in the upper atmosphere, this band of high-speed wind that sort of wraps across the entirety of the Earth in the mid-latitudes. If you turn on the Weather Channel, sometimes people will talk about the jet stream because in sort of the mid-latitude areas like the United States, the jet stream is sort of a weather maker for a lot of areas in the country. So this is something that even just your local Weather Channel might talk about. And yeah, it's this band of high-speed wind in the upper atmosphere in the mid-latitudes. There's one in the northern hemisphere, and there's another one in the southern hemisphere. Reminder that we're on this aquaplanet, so we don't have any land here, unlike the images I'm showing in the background. We're going to idealize this jet stream to be perfectly straight across the globe. So you notice that the jet stream in the previous images were sort of wavy, like they are in the real world. But in this idealized aquaplanet, we're going to make sure that these jet streams are perfectly straight across. So right now I'm showing you a global image of upper level wind speed in meters per second. And you can see that we have a northern hemisphere jet stream and a southern hemisphere jet stream that are perfectly straight. Because we're going to be looking at systems like these extratropical cyclones, I'm going to introduce two other variables, which we're going to be looking at a lot for the rest of this talk, which are sort of surface pressure, or rather a variable that is a proxy for surface pressure. And what this is useful for is it's useful for locating the centers of these sort of extratropical cyclones, which are low pressure systems. So in a map of surface pressure, you'll be able to identify the center of this cyclone. Additionally, we're going to be looking at upper level temperature, which allows you to see how this cyclone is manipulating the temperature field and how it's drawing energy from it. So these are just variables that I'd like to introduce now so that you're familiar with them for the rest of the time here. Okay, so you'll notice that these initial conditions are stable atmosphere. They're zonally uniform. Zonal refers to variation in the east-west direction. So you'll notice that sort of everything is the same left to right. We're going to fix the sea surface temperature here. So again, there's no moving ocean. We're just going to fix the sea surface temperature at a specific setting. And there's no radiative forcing. So we've essentially turned off the sun. So because we don't want try to remove any external energy from coming into the system. As I said before, this initial condition is a steady state solution of the equations of motion, but it's unstable. So ideally, a model should be able to keep this ball on top of the hill, the ball being our atmosphere, but not all models are perfect. So this first part of the test evaluates the model's ability to do this. Assuming it is able to do so, what we can do is we can kick the ball off the hill in a controlled way by adding a Gaussian perturbation to the wind speed field. So we take our nice idealized wind speed field here, and we add a tiny little Gaussian perturbation of 1 meter per second at a specific location, and we see how that propagates into a fully developed storm. We apply this wind speed perturbation uniformly with height, and it triggers the development of our baroclinic wave. As I explained before, it's sort of our extratropical cyclone. To give you a sense of what this might look like, sort of as a preview of the results, here I'm showing you the surface pressure field with a star locating where the initial perturbation is placed. And here I'm showing you the surface pressure field 10 days later in the simulation. And so what you can see is that there's some interesting downstream development to the east of where the initial perturbation was placed in the star. And specifically, what you can see is that there's 2 low pressure systems there, which are exactly the extratropical cyclones that we're talking about. So even though this is sort of related to that, even though we're on this aquaplanet world, this made-up world, the weather systems that we're looking at are analogous to those that we see in the real world. Okay, and it's worth noting that models must be able to maintain the steady state before attempting the second part, because if the ball rolls off the hill sort of on itself, then you can't test the effect of you kicking it off in a controlled way. Okay, so now I'd like to talk to you about the model that we're using, which is called the Deep Learning Earth System Model. It's a model that's been developed in Dale's group in the Department of Atmospheric Science for the past few years. A full overview would be a little too much for this talk, but the key here is that sort of the key innovation of the Deep Learning Earth System Model, which we call DeLeSim, is that it was the first machine learning weather prediction model to be stable over the course for rollouts of 100 to 1,000 years, which is key because for a long time, many of those models weren't stable for anything past a month. And so if you want to have something for like climate simulation or studying internal variability in our system, you need this stability. So that's sort of the innovation of this model. So the model operates on what we call the Heel-Pix grid, which involves these 12 diamonds, which you can see here, that you sort of stitch together on the globe, on the sphere, to form this discretization. And then in order to get higher and higher resolution, you subdivide recursively those diamonds to, by 2, 4, 8, 16, and so on. The deep learning model which we work with is a convolutional U-Net. Essentially what this means is that the model has a couple layers in it. The top layer captures small scale motion and the bottom layer captures our largest scale motion. And information passes through the neural network in sort of this U shape so that I can capture both the small scales and the large scales. This is an architecture that is borrowed from traditional computer vision techniques where, sort of different things that are far away in an image might matter for detecting what's going on in one part of the image. And so you want to be able to capture both what's near you and what's far away from you. What's worth noting is that DeLeSim is exclusively trained on real-world weather data. We don't retrain it for these aquaplanet simulations, so we're sort of throwing it in the deep end to see what it has learned on its own from real-world weather data. Okay, so let's talk about some results. So here we have part 1 of the test. Here's our surface pressure and our upper level temperature field. And recall that the goal is to be able to maintain these conditions as long as possible. So here's at 0 days, and here's it at 10 days or 8 days. What you notice is that we didn't do a very good job of maintaining the initial conditions. Something's gone very wrong on the right. But there's still something interesting to talk about here because it's a very regular pattern. So we can sort of dissect what's going on here, which is sort of one of the powers of these idealized simulations, that you can sort of get a better sense of why the model is doing the thing it is. Okay, so one thing we notice is that we have what we call a wave number 4 pattern in both hemispheres. It's called wave number 4 because it repeats 4 times going across the globe. You'll also notice that the evolution of the system is asymmetric in the northern and southern hemisphere, even though the initial conditions were symmetric. So these are telling signs. And while we weren't able to maintain the initial conditions like we wanted to, I still think this result is interesting for a couple of reasons. In order to contextualize that, I'd like to compare sort of the results of DeLeSim, our model, versus another machine learning weather prediction model. So here I'm showing the 2-meter air temperature simulated by our model on this aquaplanet at 5 days. And here I'm showing the same field at 5 days for a different machine learning model called ForecastNet. They're very different. One thing you might notice is that ForecastNet simulation has continents in it. It has Australia very clearly visible. You can see the Indian subcontinent and to a lesser degree, the North and South America. But remember that we initialized our model on an aquaplanet. There's no land. There was no land in the initial conditions, but the model has sort of spuriously regenerated the imprinting of the continents in it. So even though DeLeSim wasn't able to do exactly what we wanted it to do, it's still impressive that it was able to maintain aquaplanet conditions without regenerating back to the training data that it was trained on. Because remember, it was only trained on real-world weather data. Further contextualizing this, we can talk about, we can compare DeLeSim's output with that of traditional models. So traditional models are nominally supposed to be able to pass this test, but models are perfect, and people actually use this test in order to find problems with their traditional models as well. So here's the surface pressure at 9 days for DeLeSim. And here is the surface pressure field for 2 models that do very well on this test. So you'll notice that they haven't broken down into any regular pattern like DeLeSim has. They've maintained this zonally uniform, so no east-west variance in their results. So these 2 models did very well. But there's 2 other models which don't do very well. In fact, they sort of break down in a similar way to our machine learning model. So really the takeaway here is that DeLeSim's aquaplanet simulations are at least qualitatively comparable to traditional atmospheric models. Some do well, but some don't. So I think this is still an impressive result, even if we weren't able to maintain conditions that look like this. But ideally we do. So I spent a lot of time looking at this pattern and thinking, are there ways that we could do better? Are there ways that we could improve our machine learning model in order to have it satisfactorily pass this test? And over the course of a lot of iterations, I found that yes, there are ways that you can make informed improvements to our model in order to have it respect sort of the solution that we expect. So these details are a little dense, but through looking at the outputs of the simulations, I was able to find a couple problems in the model that I'd like to talk to you about now. So one of the first is that when our model hit the seams of our HealPix grid, sort of shown in red when the diamonds come to be stitched together, as the model came to those seams, it would treat those grid cells differently from those at the interior of the faces, which are shown in green. So essentially the pixels along the red seams are being treated differently than the pixels in the green, which led to, there's 4 seams in each hemisphere. That was why we were seeing a regular repeating 4 pattern in the atmosphere. We also noticed that the simulations were not symmetric in the northern and southern hemisphere, even though the initial conditions were. And so I thought, is there a way that symmetric inputs should yield symmetric outputs in the model? And I found that there was a way in the machine learning architecture to ensure that if the model sees a symmetric input, it should give a symmetric output. But if it sees a real world weather state where the input is not symmetric, then it should give an asymmetric output. And by sort of enforcing this principle in the model, it's sort of like a physics-based constraint. We know that the dynamics of the atmosphere, the equations, have this symmetry about the equator. And sort of encoding that into the model actually allows it to be a better weather predictor on both the real world and our aquaplanet world. So it's sort of a best of both worlds thing. So I'm wrapping these changes into a new model, which I call DeLeSim AQ. AQ is for the aquaplanet. And we can sort of look at how this model does on our test now. So back to our initial conditions, we have surface pressure and upper level temperature, and the goal is to maintain these. So with our improved model, how do we do? So this looks a lot better, especially when you're referencing DeLeSim AQ's results to the original, where we no longer have this breakdown of the initial state. There's definitely some drift, but I think that this is a satisfactory result given that this is what we were originally looking at. So we've maintained this sort of uniformity in the east-west direction, which was part of the goal of the original test. So the takeaway here is that Delisum AQ can reasonably maintain the initial conditions, and that it's satisfactorily passed part 1 of the test, sort of keeping the ball on the hill. So now we get the chance to knock it off in a controlled way. Recall that we're knocking it off by putting a small perturbation on the wind speed field, and we want to see a cyclone developed in response. So what you'll see is that, so we have our initial conditions here, and after putting in our tiny perturbation on the wind field, 10 days later, we see some interesting development in the box there downstream of where we put the initial perturbation in on the star. Zooming in into the box there, we have our initial conditions and our result 10 days later. And what you'll see is that we have sort of in the surface pressure field, 2 low pressure systems that are associated with extratropical cyclones. And we have sort of strong fronts that are associated with the extratropical cyclone sort of whipping up warmer temperatures from towards the equator towards the poles, which you can sort of see in the temperature field there. I think maybe, how much time do we have?
You maybe start wrapping
Yeah,
up.
sure. Yeah. I honestly think this is like a fine place to end. Really, the takeaway here is that Delisum with modifications, with sort of informed modifications, can capture the realistic physics that we hope an atmospheric model can, and sort of it's telling us that it's extracted sort of generalizable atmospheric physics from real-world training data instead of just learning spurious patterns in data. And this is desirable for a number of reasons, in that it can increase our trustworthiness in the model. We can be sure that, you know, in future climate states where sort of the distributions of temperature and so on have shifted, that it's going to make the right answer because it's ingested the right physics. Yeah, sure, we can end it there.
Questions for William, and if there's any online questions, I can read those to William, or he might actually see them as well.
Yeah, I might see.
Yeah.
Eric?
Yeah, so the lessons that you learned to change Delisum to be able to maintain the steady state, do you think they're generalizable to other architectures of these deep learning weather models, or do you think it's like because you have this field fixed grid that you want to do?
Yeah, I think some of the changes are generalizable to other models. So our model operates on a specific grid, but other models, say, operate on different grids. And having talked to the developers of some of them, they've seen grid imprinting from those models, even in real world data. And so I think that those would be even further exposed if you did this idealized simulation, because sort of the uniform nature of these initial conditions very quickly exposes grid imprinting problems in the models. And so I think that while the specific fixes they might need will be different, sort of the general problem of grid imprinting, both on Aquaplanet and in real world simulations, would become evident with these, and they could maybe use that to inform the change to their model. Yeah.
Could you talk more about how you modify the Delisum to Delisum AQ?
Oh, yeah, sure. So for the HelioPix grid fix, essentially what was happening is that, here, maybe I'll point with the mouse so people can see on Zoom, is that I needed to make sure that the model saw the right, if you're looking at this gray pixel here, I needed to make sure that it saw the right pixel across the seam. Everything was just the way it was coded up. Maybe you could argue it's a bug, but the way it was coded up is that the pixels were being a little offset. So this pixel here on the right, in the gray, was seeing the wrong pixels across the seam. And so sort of aligning those correctly made sure that the model was able to maintain the east-west uniformity. I hesitate to call it a bug because it's sort of just a modeling choice in the original architecture. And the machine learning model is able to sort of still make the right prediction on real world data, even given this sort of idiosyncrasy. But for these Aquaplanet simulations, it causes problems.
So you actually not retrain the model, you fix the bugs here,
And
you use the weights of impression on the ER5.
So I actually did retrain the model, but I haven't tested what would happen if you trained it with sort of this this one grid, this one way you lay out the grid, and then you apply it without retraining to another. Yeah, I'm not actually sure, but because I retrained it. Yeah. Dominic?
So it seems that the baroclinic wave test is important for weather prediction and getting individual systems right.
Yeah.
But you know how important it is for climate prediction and like the stability and the mean state?
Yeah, I think so. There's the test as is definitely for weather prediction, and sort of we are making a little bit of a leap in saying that it's helpful for climate prediction because, you know, if we expect that the governing equations in 2100 are the same that they are now. And so if it's learning the right governing equations, then hopefully it'll be able to generalize. But I think there's definitely some changes to the test that you could make in order to test behavior in future climates, just like increasing the sea surface temperature, for example. Like the sea surface temperature right now is sort of set to current day conditions. So, but we know that the sea surface temperature is going to rise in later climates. And so you can sort of do plus 2K SST simulations with this planet and evaluate how that changes the evolution. That's just an idea. I'm not sure if that's actually how applicable that is, or if people do that with traditional models, but that's one idea.
Do you have an intuition for like what about the DLE architecture makes it able to generalize real world?
Yeah, I've thought a lot about this, especially this result, because I suspect that DeLeeson was designed with the principle of not having any locational information in it. So a lot of machine learning weather models, for good reason, take inspiration from computer vision, machine learning, deep learning for computer vision models. For example, in a transformer model, you often give the model positional embedding, so it knows the locations of each of your words in the sentence. When those models were adapted for weather prediction, you sort of give the model a locational embedding of like this latitude and longitude. And so that makes sense when transferring models from sort of natural language processing to machine learning. But in reality, it just gives the model the ability to memorize the temperature over Australia. And so even when the initial conditions do not have Australia in it, it's learned from the training data that it's going to have an easier time predicting the temperature over Australia if it sort of memorizes a background state of the temperature over Australia. And so I think not having those locational embeddings in DeLeeson definitely lend it some ability to generalize. I think there's some other things too, but I think that's the main one. I don't think there's any questions online yet, but.
Any of these idealized testing scenarios be used as training data for your model as a way to embed these architecture? Definitely.
I definitely think that would help. So I've thought about sort of if you take the simulations from a traditional atmospheric model on an aquaplanet and give them to the machine learning model, it might improve even real world weather prediction. It's sort of just like having more training data helps. I think that for the purposes of this study, the goal is to sort of see what it could learn without those, sort of how well can it extract the right physics from all the complex real world data. So for the purpose of this study, we don't want to give it any traditional atmospheric simulations, but I think if you just want to make the best weather prediction model, it might actually be helpful and there's a lot of other sort of idealized simulations on the hierarchy. So there's sort of a really wide range of these simulations from traditional atmospheric models that you could give to your machine learning model as training data, but I don't think anyone's really explored that yet, but it's definitely an interesting path.
So how close are we to having ML weather models in practice, or do we already have them and it's just a matter of getting them to work well on longer timescale?
So for weather prediction, I would say that we're there. I like the weather on your. I'm not exactly sure if like the weather on your phone is yet an AI model, but sort of institutions like our National Oceanographic and Atmospheric Administration and the European equivalent have operationalized machine learning models already, meaning that they give the same initial conditions they give their traditional model to a machine learning model, and you can get the forecast from both on their publicly available websites. So I would say for weather prediction, we're there. For sort of climate simulation, that's where things are sort of getting, people are working on right now, because it's only been, I don't know, a year or so since we've been able to stabilize these models for longer rollouts with some innovations in the machine learning space. So that's where people are sort of kicking out right now.
All right.
Just one last question. So is DELISIM designed mostly for climate or weather or just the whole scale? And I'm just curious, you know, since like you've got this ForecastNet 2 there with Australia in there. On a 5-day forecast, do you have any sense of who does better, you know, over temperature over Australia, your model?
Yeah,
ForecastNet?
it's a good question. So our model is only trained to predict the weather. So it's only trained on 24-hour chunks of the weather. So you give it an initial condition, it predicts the weather over 24 hours, and you have a bunch of those examples in your training data. So I think part of what we're happy about is that the model is able to do so well on its climate simulations, having only been trained on short-term weather. And if you're asking about the 5-day forecast here, ForecastNet 2 does better, and 5-day predictions of real world weather. But I think part of the reason it's able to do so is that it's able to memorize sort of patterns in locational patterns in the data. And so it doesn't have to just predict the atmospheric dynamics. It gets to cheat and say, I know that the historical weather over Australia has been this much, and then predict sort of a change on top of that because you're giving it locational embeddings. And so, yeah, I think that it does better, but maybe for the wrong reasons.
All right, great. Right, yeah, thanks so much again. And thanks everyone for coming. And we're gonna wrap up this evening.
Great job.
Thank you. Thanks for having me. Appreciate it.